So this question is uh, kth smallest suburb sum. So what we have to do here is that like in basic sense what we have given here is that we have given a array, let's say 2, 1 and 3, and we have given a k value. So what we have to do is we have to find uh, first, let's say what is the subarray we have here. So it could be 2, it could be 1, it could be 3, it could be 2 1, it could be 1 3, it could be 2 1 and 3. So these are all the subarrays we can form from here. So what's basically we get from this is that we get 2 1 3 3 4 and 6. So if we sort this, we get 1 2 3 3 4 and 6. So what we want is the kth smallest subarray. So we want the first, the second, the third, the fourth, the fifth, and sixth. So we want this as our answer. If the k equals to 5, then we want this as our answer. So, so like what we have to do here is that basically we initially we can think of it as like we can just do it brute force with like n of n square time with this as thinking of starting from the initial like uh, like many of the surveys it can form from that array, and then sorting them, and then uh, we can just push it on like some kind of heap, min heap if we want to maintain, and like we can somehow like make uh, like get to an answer in that way, but it would be too slow because the constraint is given here is too large because n could be up to 10 to the power 4, and a a k could be like k is also very large given here, and like k could have been like you have to find the last, so let's say 6. So it could be like you have to go through all of this to get to this, so it will add up to a very large number of time complexity for that as well. So we can do it here with this way. So one thing we can see here is that instead of thinking of this is in this questions, like we should think uh, like okay, so there is a way, let's say a I have a sum, like the sum, let's take we have a sum, so any sum we can take. So if any sum we can take, and that sum we can say that like if this sum is like our answer, so this sum is our answer, so it could be from this or it could be from this. So if that subarray is our answer, we don't have to find that subarray as like you have to do like one of the thing is that you don't care about other subarrays because you have to reduce this number of subarrays, like you don't have to check this or you have to don't have to check this. So that is one of the intuition you have to follow, and one thing is clear here is that uh, to possibly like we can think of it in a bit reverse way. So what we can think here is that what is the smallest sum, like the sum, anything you can take like so sum t, such that there are at least k subarrays whose sum is less than that. So we want there are key subarrays, like we want such subarrays which are less than that. So we want the subarrays like the count of it and the sum count, like you can say the sum count which is less than that, the the sum count of t. So what this basically means here is that uh, so you can think of it as like, okay, there could be the minimum number of subarray which is possible is the least value from here, and the maximum sum it is possible is the sum of all the values. So sum of all the values is 6 here. So we know that it can't exceed from this and it can't decrease from this. And we also know that we wanted to search in a sorted list. So we basically care that sum, does that search we have pull up, does that fit in this kind of scenario or not? Because we can reduce the search, like if we have found a answer for that, okay, then we will search here. We doesn't require to search in the right side part of that. Only the left side part is important to us for that. So during this, we can one of the things we can see is that uh, the left side part of the search is only important thing that is in this question, as the right side part or any part, like you should be able to determine where you are searching based on the decision you are taking on a optimization. So that optimization problem, like any kind of optimization problem here, requires you to do that. So we can just binary search over that, and to found this, like the count of that server is less than or not, we can just use two pointers. So like how we are going to be doing it. So like let's say anywhere, like anywhere, like you wanted to uh, like, okay, this sum is possible or not, from this is like you take any kind of like sum from that. So it could not happen also, like it is totally possible it could not have happened. But let's say you have a array. So what we have to do is this in the two pointer is that we will just fix that r and like move it till the end, and the left is also be going to be here. So we will increase that r until like it is less than the sum we have. So when the r is greater than the sum we have, so we have to decrease this l. So r is going to be plus plus and l is going to be minus minus when so basically it depend the two pointer approach is like you will find a subarray that is if the possible sum is available or not. So like you will get that number of subarrays which are possible from that, and we can just count it by like r minus l plus 1, like how many subarrays are possible from that range. Because you know that this many subarrays is possible in that range, so you should be able to make that kind of subarray. So it is totally based on that. So like like these all are possible subarrays here. So you can see here that these all are, so these all are possible. Let's say like if for example like these all are possible subarrays, so you want to count them all, so you can just basically do is that you know that this subarray is possible. So we know that we should count all of the like the possible like combination of the subarrays which we get. So we get is r minus l plus 1. So the possible in not in combination of combinatorics, but the way we are finding this out is just a two pointer approach, and you are able to code this up very easily. So for coding this up, uh, one thing is important in is that we should remember that we have to find is what is the smallest sum x such that there are at least k subarrays whose sum are less than equals to x, like you can say. That is the important part of that. So this problem is based on that. So to we can code this up very easily. So first we take like any the the lower value which are we going to define. So any lower value uh, which we can get a sum is going to be 0, and you can always go to the higher value for the sum to be the subarray of that to be like you can say like 9. So uh, whenever like we just write a binary search here, a simple binary search, and and like if like we will just make a assume like this is a function we have, and we will just make a function for that, and is greater than equals to k for that, and if this is like the count we got is greater than equals to k, so we can just increase this, like we will just reduce our search space for that. Otherwise we will just like search over the next. So this is basically what the binary search are going to be doing here. So how we are going to be, and we will just return here the low we have found for that. So we will just return low here for what we have found. So how we are going to be writing this like the count server function. So it is basically a two pointer approach. So we'll just write it as a so const, because we don't want to change the vector inside what we have like for that, and we don't want to make copies for this as all the time, so we will just use that. So let's say like we can initialize a count variable to 0, some variable to 0, and it'll like the starting position to be 0. So for like we can say less than the nums size like till end we want, so we will just like increase our r until, so like we will just increase it, like we will add that new expanded window like the increase window to our sum. So then what we can do here is that we can just add it to our count. So what count we will get is that r minus l plus 1. So this is the count number of subarrays we can form from that sum for that. So one thing is more important here is that if like our sum increases the target, so what we will just do here is that we will just reduce our sum. So we will just reduce our sum like the nums uh, for the left side. So we will just reduce it because like we are shrinking the left portion for that. So we will just reduce the sum the left, so we have to shrink it. So we will just increase the left by 1 here, and after this we will just return the count here. So if you see, this is basically a code which does run on most of the machines, and it it does kind